And we're talking about 6.2, which is volumes. So maybe I'll tell you our overall goal right now is that we want to find the volume of a solid, any solid. Okay, it doesn't have to be nicely shaped. And so what you do is you work up in difficulty. We're going to start with something easier, which is a cylinder. So let's start with something simple, which in this case is going to be a cylinder. We know how to calculate the volume of a cylinder. There's a nice formula for it, and so the volume of a cylinder is given by, do you remember, V equals A times H, where A is the area of the base, and H is the height. That's a pretty nice formula. Whenever you have nicely shaped things, usually they have nice formulas for area, or volume in this case. So let's say let's do an example of a cylinder, a circular cylinder. Let's take a circular cylinder. So that's one where its base is a circle. I'm going to do my best to draw a picture for you of a circular cylinder. And the volume, well, the base of a circular cylinder, part of its name is circle. The base is a circle. What's the formula for the area of a circle? Pi r squared. And so the volume is going to be pi r squared times h. So again, the story's kind of known. We know how to calculate this volume. It's not too difficult. So again, our shift right now is we want to find the volume of other solids, not just these cylinders. So we want to find the volume of other solids that I'm going to call S. So I'm going to tell you the idea behind this process. I don't want to get into too many details about it because I want to focus more on doing problems today. But the idea is the following. Well, we wanted to compute area under a curve. We used Riemann sums because our objects were not nicely shaped. But rectangles, we know the area of a rectangle pretty easy. It's a nice formula. And so we use something nice to approximate our area. So same thing here. I'm going to use my shape is something maybe not so nice, but we're going to repeat the idea of Riemann sums here. Riemann sums for areas. So we're going to take our object and we're going to essentially cut S, dissect it into pieces, S1, S2, up through Sn. So the way I think about this, and your book describes it, is you have kind of some solid shape. Imagine you have a solid shape in front of you, and you take a knife and cut it, just like you were cutting like a loaf of bread. Okay, and you're getting these chunks that together give you your whole solid. So that's this S1, S2, Sn. There are these chunks, pieces, that when you stick them together, they give you your solid shape, whatever it is. So maybe I'll write here, think of cutting up a loaf of bread. And so then I've got these wedges, these pieces, whatever shapes they are. And the idea is each one of those, I'm going to use a cylinder to represent, to approximate that volume there. So approximate each SI by a cylinder. Okay, so we're just really redoing the idea of Riemann sums with areas, but we're doing it here with volumes, and we're using cylinders instead of rectangles. Okay, so if you do that, then what we learn is that the volume of this object, you can integrate. If your object starts at x equals a to x equals b, you can integrate from a to b, a of x dx, because remember Riemann sums, you can write them in terms of integrals if you take a limit. And this a of x here, this represents the cross-sectional area of your solid.